Okay, so today we'll look at delay minimization. We looked at logical effort in the last class, definition of logical effort, how to calculate logical effort of gates. Now we'll see how to apply that to minimize the delay of a path of gates. Before we do that, in the last class we left with this particular problem of calculating the logical effort from the data sheet, and the data sheet had data for two gates, an inverter and an AND 2, and we wanted to bet the inverter will use as the reference gate with which we'll compare all the other gates. So this inverter has a capacitance, input capacitance of 3.6 femtofarads, the AND 2 has 4.2. The rise and fall delay. What are this intrinsic rise and intrinsic fall? This is the parasitic delay. That means when there is no load, what is the delay for the output to rise? That means input is falling, output is rising, 50% to 50% point. That is the delay we are talking of. And that delay on an average is 20 picoseconds. For the inverter, 25.4 picosecond for the AND 2. And the slope is, that is this, if you plot the delay as a function of the load, the output load, that is a straight line, and that straight line has a delay of, or a slope of 3.45 picoseconds per femtofarad for the inverter, 3.68 picoseconds per femtofarad for the AND 2. That means every additional femtofarad of load you put, the delay goes up by 3.68. Again, it's an average value I'm using. As I discussed in the last class, you can calculate the effective logical effort separately for the rising and the falling transitions, as well as for each input of the gate. The answers, the numbers could be different. So let's see how to calculate this. So we'll just put down the equation. What are the two equations? The inverter delay, T inverter, is tau, is the whole technology constant, times P plus GH, right? That's what we said. P is the parasitic, G plus G times H. G is the logical effort, H is the electrical effort. For the inverter, G is 1, because that's, we are saying we are going to use that as a reference. So hence we'll, by definition, we'll call G to be 1 for that. And the electrical effort is basically the ratio of the output capacitance seen by the inverter to its input capacitance. Output capacitance is C out, that is a variable, and input capacitance as specified in the data sheet is 3.6 femtofarads. So this is the equation for the inverter. Similarly, equation for the AND 2 is tau times parasitic plus G times H. G for the AND 2 times H is again the load capacitance seen by the AND 2 divided by its input capacitance. Now, we are kind of using input capacitance of one of the inputs just for illustration purposes, and you can do it for every input. You can do the same thing. You can have a equation along the same lines. Okay, so now what are the unknowns here? G, all these are unknowns. Gn2 is an unknown, Pn2 is an unknown, tau is an unknown. C out is an unknown, but that is something anyway not inherent to the gate. It is a load you put outside. So you can kind of put whatever value you want for the calculation purpose, and that's what we do out here. Because we know that the slope, they have given the slope, average slope to be 3.45 picoseconds per femtofarad of load. What that means? When I put from C out equal to 0 to C out equal to 1 femtofarad, an additional 1 femtofarad, increases by 3.45 picoseconds. Right? The delta increase for every additional 1 femtofarad of output load is 3.45 picoseconds. So you just substitute that. Tau times 1 femtofarads, slope is tau times 1 femtofarads divided by 3.6 femtofarads is 3.45 picoseconds. So tau comes out to be 12.42 picoseconds. Okay. So once I know tau, I am also given the inverter's intrinsic delay. Right? There is a separate for rise and fall. We are just taking the average, just to keep the slide simple. So tau times P in is given to be 20 picoseconds. That's what the average came out from the data sheet. So P inverter is then 1.61. If you see for this particular cell in the textbook hopefully some of you have started reading. The P is assumed to be 1 for the inverter because the drain capacitance is assumed to be about the same as the gate capacitance. So that is why P is assumed to be 1. That is just for simplicity of notation and so on. But for this particular inverter of this in this technology, you see it comes out to be 1.61. That means the drain and the gate capacitance are not the same. In fact, drain capacitance per unit width is 1.6 times that of the gate capacitance per unit width. The drain has more capacitance than the gate per unit width. So this number could be different for different technologies. So now let's come back to NAND 2. The same thing we apply here for NAND 2. The average slope is tau times GN2 times you put in 1 femtofarad by 4.2 is given as 3.68 picosecond. Now we know everything except tau also we know from previous calculations, so we get GN2 to be 1.25. Similarly, you can also calculate PN2. So you get all the parameters for the linear delay model of your gate. So this is basically how you will calculate the effective logical effort using either measured data or simulation data. Now one thing you notice here is that in the hand calculations in the previous lecture, where we had sized the NAND 2 to have a NAND 2, we said the pull down stack, if you want to have the same drive strength, we'll make the NMOS to be 2 and 2 because there is a series of 2. Each one has R by 2, so the whole thing has R, same as that of a inverter of size 1. And when that is 2 and PMOS is also 2, the input capacitance looking into that input of the NAND 2 is 4. 4 units, 2 from the PMOS, 2 from the NMOS. For an inverter, the input capacitance is 3. 1 from the NMOS, 2 from the PMOS. So just by kind of sizing and hand calculation, you would expect the logical effort to be 4 by 3, right? So that is what you would expect, 1.33. But for this gate, at least from the data sheet, it is different. It's less than 1.33, it is 1.25. Why is that? Well, it's because of this velocity saturation. This is something which comes to help you. Normally velocity saturation is bad because you don't get enough drive strength. Instead of the current going quadratically as the gate overdrive, it grows as a factor alpha, which is less than 2. Vg minus Vt to the alpha, right? That is the equation for current in saturation for a transistor which is in velocity saturation, where alpha is less than 2. In the extreme case, as we had discussed, alpha can become 1, and really the current in the saturation region is just given by this equation: W times Cox times velocity saturation times Vgs minus Vt. If you notice, there is no L here. Normally current is W by L. L is gone out of the picture here. That means the transistor is completely velocity saturated. The current is independent of L, which means that when I have a series stack, whether I put one transistor or two transistors, because in a two transistor length is effectively double. That is why for a NAND 2 we had double the width, because we said length is double effectively, so overall width of each one should be double. Here, when I put the series stack and there is no degradation in current, why should I double the width? I'll leave the width the same. I'll use the same one size transistor for a series stacked gate also. So a NAND 2 then will have a NMOS of size 1 and 1 because it's not degrading. So that means the input capacitance looking into any of the inputs is 2 plus 1, 3, same as that for the unit inverter. So the logical effort for a completely velocity saturated NAND 2 gate is just 1, same as that of the inverter. So it's less than 4 by 3, it's 1. So that is why, and for transistors which are not fully velocity saturated but partially velocity saturated, you are somewhere in between. Okay, so the velocity saturation comes down and affects the logical effort calculation. So now let us say take a path or a sequence of gates. and the question is to size the gates. Okay, such that in this case we are looking at to minimize the delay. We want to have as fast an operation as possible. Now, if you see, so what are we doing here? We are basically we are what we will do is in this we'll have these gates which have a certain template, as I discussed in the last class, where the relative sizing of the transistors within a gate is fixed. Relative sizing, but the absolute size, which is essentially how I scale the gate, how I scale every transistor in the gate, is what we want to determine. Now, how would I do the relative sizing itself, you might ask. For example, in the case of a simple inverter, I want to maybe keep the pull up and pull down resistances to be the same. Hence, I'll make my PMOS to be twice as wide as that of the NMOS. So the relative sizing is PMOS is 2, NMOS is 1. In the case of an AND 2, same. I want to firstly have equal pull up and pull down resistances, and plus pull down resistance. Then, because there is a series stack, I need to increase the width. Here, I'm increasing the width by 2 because I'm not considering the velocity saturation case. But if you basically size it such that you have equal pull up and pull down resistance. And the template we have for this case is 2, 2, 2, 2. All transistors have the same width. For the NOR 2, because there are two series PMOSs, I have to double the width from that of an inverter. Instead of 2, I have to make it 4. So 4, 4, 1, 1. Right? So that is the template for the NOR gate. So these templates, the relative sizing, we are not going to change because they have been arrived at with the requirement that pull up and pull down should have the same drive strength. So we are not going to change the relative sizing of the transistors. But absolute sizing, how do I scale everything, is what we need to find. So that is what is done here, where you have 10 as the size which is given and the load which is of size 20. Now what are these numbers 10 and 20? What are the units? In fact, for convenience, all numbers have been converted to the sum of sizes of transistors. 10 is the size of NMOS plus PMOS. So it is the same as the capacitance because I had to just multiply with some proportionality constant. So it's really the capacitance. Input capacitance is 10 times some x femtofarads or some k femtofarads. K is a constant, but we'll just call it 10 because we are just doing relative sizing with respect to this input. 20 is also expressed in terms of the gate sizes, just to keep everything in the same units, in same domain, so that calculations become easy. Okay, and now we have, let us look at the logical effort for the inverter is 1, G1. Logical effort of NOR 2 is 5 by 3. Why? Because you take any NOR 2, 5 and compare it to an inverter 3. 5 by 3 is the logical effort of NOR 2. Logical effort of NAND 2 is 4 by 3. Why? Because this NAND 2 plus 2, 4 divided by 3. Remember, logical effort is you have to make sure that the drive strengths are the same as that of the inverter with which you are comparing. So we have sizes such that the drive strength of each of these gates is same as that of the inverter, both for pull up and pull down. And so we can just take the ratio of the input capacitances. Final inverter is 1. And then you have the final load 20. So this is what is given to us. And we want to basically figure out how to size these such that the delay is minimized. Now typically you need to have these constraints. Input and output capacitances have to be given to you. If they are not given, then you cannot, there are many solutions. I mean, you cannot solve that problem basically. And typically in circuit design, you would have some, like for example, the input could be driven from this inverter. It could be the output of a flop. There is a standard cell flip flop which is driving it, and that size perhaps is this 10. So that is fixed. You are not going to change that, and then you have to find the size for the rest of the thing. So now you can ask the question, why is there this notion of optimum sizing also? Like, why not? I mean, if you look at any particular gate, if I take this size X here is referring to the total input capacitance seen in the gate. Okay, if I call this the unit NOT 2 gate, the input capacitance is 5, whereas this is X, some number other than 5 perhaps. If I increase X, what happens? This gate becomes more powerful because I'm scaling, I'm increasing the width. So the delay of this gate, he can drive this quicker because this load is fixed, this is going up, so this delay becomes smaller. But X is affecting the delay of the previous gate. So the previous gate will start slowing down. So while you gain, so the total path delay is sum of all these gate delays. So while you play around with X, you improve something, you degrade something. So whenever you have these kinds of situations, essentially you have to kind of see how to set everything properly. What is the right setting such that you have the best possible, minimum possible delay. Okay, so fortunately this particular problem is very easy to solve. Okay, this is essentially an optimization problem where you are optimizing the delay, and we'll see in the next slide, it's very easy to solve. How do you solve this problem? Well, you have to set up the equations. The total delay, path delay, is the sum of delays of each gate. So the delay D1 plus D2 plus D3 plus D4. That is the total delay, which we want to minimize. What are the variables we have to minimize? Well, our real variables are just basically these X, Y, Z, but we are kind of casting the problem as finding the equivalently the electrical efforts. We'll see that just makes the problem really simple. So we want to minimize, it's the same thing. If I can find H1 till H4, where each H is the electrical effort. The electrical effort for this final gate is C out by C in. C out is 20, C in is Z. So 20 by Z is H4. H3 is C out is Z, because the gate is Dan2 is driving this inverter, and input capacitance is Y. So Z by Y is the H3. H2 is Y by X, and H1 is X by 10. So if I find H1 till H4, I can find X by Z, similarly vice versa. So we just say minimize the total delay over this space of spanned by these variables H1 till H4. So this is really the optimization problem, or I can even say minimize over X comma Y comma Z this delay D. A lot of times if you are doing it in MATLAB or writing your own, it's just a brute force search. X, Y, Z, what possible values, I mean actually you have infinite possible values, but you say okay, I know that it's not going to be too large, so you take X, Y, Z, and you say I'm going to search for every value, maybe X will go from 1 till 100, Y will from 1 to 100, Z 1 to 100 in steps of 1. So you have 1000 possible values, you just try all of them. You know the formula for delay, you put everything, you get the delay. From there you take the minimum. Then you say okay, my step size is 1, let me, around that point maybe you are going to put another grid, maybe with smaller step sizes, and then really resolve and get there. So that is one approach you can use, but that kind of approach can become very, if you have a lot of variables, it can become a problem. But it's something you should not dismiss out of hand, because nowadays computers are really powerful. You can easily write this. To write such a program is very simple. Some scripting language, MATLAB, Perl, Python, whatever, you can write it. Let it run for days. What is there? It will keep on running, and you'll get the answer. I mean, there's no, you should use the compute time, and these kinds of simple-minded approaches you should not dismiss. And these approaches become very important when your delay model becomes more complex, where you're saying, okay, I'm going to now start putting in more complex model for the delay. Maybe I want to consider the edge rate, and so on. So then an analytical solution can become difficult. At that time, this simple-minded approach can help. Of course, you can also do more sophisticated optimization techniques you can also apply, which are all numerical techniques. Now let's look at an analytical approach. This problem is fortunately solvable in a simple analytical way. That is, a formula will tell you what the answer is. So we'll just expand D to be Pi plus Fi. Fi is just a new notation for this product G times H, logical effort times electrical effort. We are replacing it with the variable F, which we call the fan out. Fi. Okay. So Now if you see, G is a constant because that is the characteristic of the gate. So Hi is a variable, which means Fi is a variable. If I find Fi, I can find Hi, and then hence I can find XYZ. So my variable to be found is F1 till F4. That is, I want to find the optimal fan outs, which will minimize the delay. One thing you notice here, that when you multiply all the F's, what do you get? Product of F's is product of GH, which is product of G times product of H. You see, product of G is what? G1, G2, G3, G4, which is some constant. Because as we said, the logical effort of a gate of a particular template is fixed, independent of the size of the gate. Okay, so that is fixed. So G is a constant. So it's really, we can say it is the path logical effort. You take the logical effort of every gate in the path, you multiply it, that is the path logical effort. Now capital H is the path electrical effort, and very interestingly it also is a constant. Why? Because you just, H is H1 till H4, H1 is C2 by Cn, H2 is C3 by C2, C4 by C3, C out by C4. You multiply all these intermediate C's, cancel out, you are left with C out by C. Any path, the path electrical effort will be the loading at the output of the path divided by the capacitance at the input of the path. The internal sizes don't matter. So the product of all the F's is a constant. And you want to minimize the sum. Okay, so you have essentially you want to minimize this delay, which is the sum of F's. P's are also constant. P, because it's a, just like logical effort, the parasitic effort is a constant of the gate. It doesn't matter how you scale the gate. Right? We discussed in the last class. The intrinsic delay remains the same. So you want to minimize the sum of four variables, F1 till F1 plus F2 plus F3 plus F4, such that the product F1 times F2 times F3 times F4 is equal to a constant. And this is basically your hyperbola, right? In a hyperbola, you have that kind of a thing, where if you take the product F1 till F4 and you say it's a constant, it traces a hyperbola. Maybe in 2 dimensions it's easy to see. F1 times F2 is equal to constant is a hyperbola, and you want to find the point at which the sum is minimum, and that point happens when all the F's are equal. Okay, so all the F's are equal, and you can try to derive it analytically, but basically you can differentiate, etc., and also do it that way. Differentiate, put the derivative equal to 0, find the values and so on. But basically, anytime we want to minimize the sum with the constraint that the product is a constant, the answer is all variables have to be equal. When all variables are equal, the optimum F is such that all variables F1 till F4 is equal to F opt. Then F opt to the power of 4, because the product of all F's is a constant. So at the optimum also F opt times F opt times F opt times F opt 4 times is also the same constant GH. That means F opt is 1/4 of GH. So once I know F opt, now I can calculate each of the H's. Why? Because it's like chaining back, because I G4, because all GH's are equal to F opt. So what I do is, I know C out, I know G4, I can get C4 because I know F opt. Okay, once I know C4, I can find C3 and then C2 and C1. Once I get C2, and then you just check and make sure G1 C2 by Cn is equal to F opt. It's just for checking. That's how you calculate all the C's, all the H's, all the C's, and then you get X and Y. So it's very simple. Everyone should have equal fan out, equal stage effort, rather, that is the correct term, technical term, stage effort. Everyone should have equal stage effort. Stage effort is logical effort times electrical effort. Everyone should have equal stage effort to get minimum delay, according to this linear delay model. So let us put these numbers here for this. Example, G times H is, G product of G's is 1 times 5 by 3 times 4 by 3 times 1, 20 by 9. And electrical effort is 20 by 10. So you multiply everything, it is 40 by 9. So the optimum effort, stage effort, is 1/4 of that, because there are 4 stages. So you are spreading the work. Each one does the same effort, so that the total effort is kind of spread out equally. Each one does the same effort of 1.45. Now I have 1.45. I put it in. I calculate x, y, z, which are the input capacitances. I get z is 13.8, y is 12.7, x is 14.6. Now that I have z, now I have x, y, z, I can calculate the sizes of the transistors. Because, in this template of an OR2 gate, a PMOS is 4/5. The total the amount of capacitance provided by PMOS is 4/5, and that of NMOS is 1/5. So when I am told that the total capacitance of the input is 13.8, I allocate 4/5 of it to the PMOS, 1/5 to the NMOS. That's how I find the individual transistors. So like that I find the size for all of these guys. Okay, just going through these equations.
Maybe not according to the linear delay model, but
right. So the question is, the commercially available logic synthesis tools, do they do the optimization, and if so, what do they do? How do they do the optimization? You're right. Yes. So because when we synthesize a particular logic description, because you typically write digital circuits in Verilog, VHDL, one of these high-level languages, then the commercial tool will take that and figure out what is the logic gate, which will realize that, as well as find the sizes of the gates. And not only that, maybe ordering, a lot of optimization it does. And because when you synthesize, you have to give a certain delay constraint. You have to say synthesize to meet a certain delay. So it's essentially and what do you minimize basically? So there the optimization problem is a little different. There what we are saying is, you meet the delay, but you minimize power, or you minimize area. Area and power are related mostly, so you want to minimize area or power while you meet a certain delay constraint. So that is kind of a more general optimization problem. So the optimization formulation will be minimize, while minimize, how will we pose the optimization problem? Minimize x plus y plus z, subject to the constraint that d is less than or equal to something. That would be the optimization problem. And whatever linear delay model, whatever model you use, in fact, so you have to kind of solve that particular optimization problem. And I believe some tools like Mentor's tool does use concept of logical effort to do that solution, but not everyone. Everyone has their own way, because depending on the sophistication of the model, they have to use sophisticated optimization techniques, numerical optimization techniques to solve it. So as a designer, really you don't get down to the level of figuring out the sizes in that type of scenario. But if you're not meeting timing, you have to look at the architecture. Maybe you have to change the amount of pipelining, maybe you have to do things in parallel, things like that. But when you do circuit design, or you do custom circuit design, maybe you're doing the design for a processor, where a lot of the custom circuit design is done. That's where the designer themselves have to figure out the sizes for the transistors in these parts. So that's when you use these kinds of concepts to come up with the sizing, at least the initial sizing, and then you can give it to an optimizer to do final fine tuning. The other thing also is important is that when you use any of these tools, okay, you have to have a way of somehow doing a sanity check, because at least in the beginning you cannot blindly trust what the tool says, because maybe you have used the tool wrongly, maybe you have set up the conditions wrongly. So you have to have a way by which you say, yes, this is making sense. I expect Uh, if I'm really having a low delay, then kind of effort should almost be the same across and so on. So you kind of look at the sizes and really see what's going on. So some of these concepts also become useful for you to be able to do some sanity check on the tools. So what we have said is that we can take a large any path as a large compound gate which has a path logical effort, which is the product of the logical efforts. There is a path electrical effort, that is C out path divided by C in path, and there is a notion of a path effort which is just the sum of the efforts of each path. But I can't push this. I cannot write f in general. In the last path, example path, we could write f equal to capital G times capital H. But in general, I cannot write it that way, especially because I can have paths with branches. Say, take this example. In this example, you have this inverter which drives two inverters, each of the same size. And then each one in turn drives a load of 90. If you put the equation for this inverter, D1, C out for this is 15 plus 15, C in is 5. That is H, G is 1, and parasitic will, as we are assuming for these kinds of discussions, is 1. So this is D, this is the delay of this inverter. Delay of this inverter is 90 by 15, that is the electrical effort. Logical effort is 1 plus 1. So in this example, if you what is happening is that the total effort is not just 90 by 5 times, is not just 90 by 5. The total effort is something more because of the presence of this branching out here. In between, in the path, there is extra load which is hanging off the path. So what you have to do is, the way to solve these problems is to actually go back to the basic linear delay equation for each gate, as we just said out here. You set up the equation, you take the sum and you minimize the sum and you get the answers. For example, here, one, you can, this is just we can also write it in this way: Ci plus 1, the electrical effort of gate I is Ci plus 1, which is the gate in the path, plus any loading off the path. That is the total C out for this gate, divided by its input Ci. So that we can write it in this form, where Ci plus 1 by Ci times Bi, where Bi is the branching. If I am branching, if there are two copies of itself here, branching is 2. 4 copies, branching is 4, and so on. So if I have circuits where there is this symmetry, where I have copies of this gate of the path, then you can just look at it and then write the overall effort as B times H, where B is the degree of branching. Okay, but that you can do in special circumstances when you have symmetry like this. Right? Otherwise, you just go back to the basic equation and just write it in this form. You just look for every gate, you see the C out by C in plus the parasitic, that gives the delay, and you set up the equation for the whole path and then you minimize. Now, if you had the opportunity to also add stages. So what is the lesson we have learned so far? What we have said is, if someone gives you a path and says what is the minimum delay of the path, the minimum delay is achieved when the effort at each stage of the path is equal. Okay, that is the optimum condition for delay. In addition, suppose someone says, look, you have this path, I want you to minimize the delay, you are free to add more stages if you want. Then it turns out the optimum effort, in the previous case all you could say was optimum effort should be equal for each stage, but we don't know the exact number for the optimum effort. That is essentially dependent on the total path effort, right? GH or GBH, as we said, divide, and then you have to take 1/nth. If there are n stages, 1/nth of GBH is the per stage effort. If you are allowed to put more stages, then it turns out the optimum effort is about 4. Okay, it's a number, constant number, which is kind of interesting. How does that come about? Well, let's look at this, right? You have let's go back to the basic equation. Fi plus pi is the delay of each gate, and there are n gates, capital N. Okay, and the product of all the efforts is constant because there is a path, there is a certain path electrical effort, there is a certain kind of branching which is there, and let's say the branching is also fixed. Okay, that means there is a certain symmetry. I mean, I fork out to 2 copies at some place I fork out to 4 copies, and so on. So I have the total branching, electrical, and logical effort is all fixed, but I am allowed to change the number of stages. Then we know that no matter what number of stages I use, from the previous calculation we know all stages should have the equal effort f opt. That much we know. So for any given n, the optimum happens when f1 equal to f2 equal to fn equal to f opt. So with of course that f opt to the power of n is equal to the total effort GBH. Then the delay of the gate of this whole path becomes, if you just, because each of fi is the same, right? Every fi is equal to f opt. So there are n of these. So delay is n times f opt plus sum of parasitics, where f opt is given by 1/n of this. Now we are saying we can also change n. Okay, I kind of jumped. So I can change n by adding extra inverters perhaps, right? So then what I do is, I have another equation out here. The delay as a function of n, for any given n we know it is equal effort. Capital F is the total effort. Now I am replacing GBH with capital F, nf to the 1/n plus parasitics, plus if let us say I put some extra inverters, n minus n1 pin. So now you can minimize this equation as a function of n also, because here capital F is a constant. It's just a property of the whole path, product of the logical effort times the electrical effort. So F is a constant. What is a variable is the number of stages, and you just do differentiate with respect to n. You get some equation like this. For example, here it is d, capital D by dn is f to the 1/n plus n times derivative of this, which is log f times minus 1 by n squared plus p. Okay. So f, and we know that, so now we'll just replace f to the 1/n by the small f, and you get this equation, and we know at the minimum d by dn is equal to 0, so this becomes equal to 0. That means at the optimum f opt times 1 minus log f opt plus p in is equal to 0. Now if p in is equal to 0, let us say we ignore the parasitic, then this equation f opt, if you solve this equation, f opt is equal to E. E is what, 2.7 something, right? So you see that if you have no parasitics at all in your logic gates, there is no the self delay, the intrinsic delay is 0, then the optimum effort per stage is E, where you are free to use as many, and accordingly you use the number of stages. So when you use f opt is equal to E, then you have to figure out what is the right number of stages to use. How do you figure it out? You know that f opt to the power of n is equal to total effort. So n is log of the total effort to the base f, because f to the n opt is capital F. So that is how you size, where you say everything is, the effort is of everyone is E, it's independent. So this is like a universal kind of law in some sense. If you're allowed to choose the number of stages, then the best way to size up is to have a multiplying factor of E. Of course, Pn is not 0. If Pn is equal to 1, then f opt is about 3.5. And if Pn is more than 1, as we saw 1.6 and so on, f opt is a little bit more. And so that is why we basically, and if you plot this, the delay as a function of the f opt or the number of stages, which is kind of equivalent, because when you have one, you have the other. There is a kind of shallow delay out here. That means, f is 3.5, 3.8, 4, etc. It's kind of, the delay is small. I mean, the delay is kind of close to the minimum. And so we kind of use this rule of thumb that the optimal sizing of a chain of gates should be such that the effort by each gate is 4. Instead of saying 3.5, 3.8, you just say optimal effort is 4, because answer is kind of close to that. And if you use 4, you will not be too far off. You can basically use 4 and, So how do we do the optimal sizing then? The way we do it is, someone tells you, okay, this is the path. This is the load driven by the path. This is the input capacitance of the path. And okay, there is some branching and so on, so you account for that. So you have a total effort for the path. Then and you are allowed the freedom to put as many inverters as you want. Then what you do is you say, look, I know that optimal effort is about 4. So you know the answer. So from that you figure out the number of stages required, including all the logic gates plus extra buffers. The total n includes everything. You find n, then you work backwards. So it becomes a very simple way to size for minimum delay. Now you can ask the question, the capital N is log of f to base f. So it need not be an integer. N should be an integer, right? Because you have to have integer number of stages. So what if it's not an integer? You get some real number, you quantize it to the nearest integer, maybe one above, one below. You try out both. It's so easy, you can just do both. Of course, you might have a requirement of a certain logical, maybe if you put odd number, you will get inverted value, so you have to choose even one. So you go to the nearest even. Right? So that's how you basically do the sizing. One thing I want to emphasize here is that sometimes, when you're coming from your BE, ME, etc., you are very used to calculating answers to 4th, 5th decimal places because you have a calculator, right? You just type it. A lot of times when you do actual practical engineering, you have to get there, okay? We don't care, okay, one stage less, one stage more, okay, functionality has to be correct. Maybe you are a little bit off. Maybe you have 4 picoseconds extra, your friend got versus you, at least in simulation. But when you put there, there are so many other things which come into the picture that those kinds of things get wiped out. Of course, the art is to know when to be precise and when not. So I don't want to kind of use it as a blanket statement, but I do find that a lot of times, because we have not closed the loop with the physical world, you tend to worry too much about 0.1 picoseconds. He has got 0.1. It doesn't matter. It just get wiped out. So you have to kind of know when to kind of do approximations and get moving, and when to kind of really optimize. And that is a case to case and based on experience and so on, it will kind of become clearer. Yeah.
With the freedom of availability to this number of things, is it possible to use number of branches also?
Number of branches? No, number of branches will not be, that is a property of the logic structure. It's already there. There is a certain logic function you have to implement. Okay, and the synthesis tool, or maybe you are the synthesis tool, your brain is the synthesis tool, and it has figured out how to implement that logic in terms of what gates to use and how to connect them. So once that is fixed, the problem is sizing. Okay, if you don't try to kind of change that, because then the whole functionality could change. Also, if you see out here, we have taken a very simple case of a linear chain, but in reality, you will have multiple inputs to multiple outputs. So one has to kind of optimize the whole thing out there. So again, by hand, such kind of optimization can become complex. So you kind of use these kinds of simple rules of thumb. If you have to do it by hand, I'll basically what I'll do is I'll kind of look at the paths, look at the output to input. I'll see uh, the ratios, and then I'll kind of use I'll see what the equal effort gives me, and then I'll basically try to use that. Now these design tools, like if you use optimization programs or synthesis tools, they will be doing this multi-input multi-output optimization simultaneously. All paths are being optimized at the same time. But the idea here is so that you get, and there are certain simple paths, certain simple symmetries which you can handle by these kinds of approaches. Like decoders, for example, there is a very nice symmetry, branching, and so on. So again, you can optimize using this concept of logical effort and this kind of analysis. So what I'll do here is that I'll come back to this example of this example where we have a multi-stage with branching and so on in the next class. And if there are any questions, now we'll, on whatever we have seen so far, we can take that.
In the first section today, we discussed that the logical effort is not equal to what we calculate in reality. But in the delay optimization topic, we are taking the ideal logical effort. So does that lead to delay and error?
Error. See, in the delay equation, see there are multiple levels of approximation which are going on. Okay, the first approximation is delay is just f plus p, where f is gh. Now you saw that that artisan standard cell essentially using the same formula. He is characterizing the whole library using this linear delay equation. He doesn't call it as gh and so on, but you see it's equivalent. We saw that. Now when I use, so so that equation has value, so that clearly that kind of those kind of standard cells are characterizing that way. Now when I have a linear delay equation, then the whole thing whatever we discussed now about how to optimize just follows immediately after that, right? The question now is what about g? How do we calculate g? So you calculate using the way we calculated for the standard delay series. So when you put in that value for g, which is calculated from the data sheet, your answers will be accurate. Now you can ask the question, is the linear delay model itself how good it is, right? It turns out this kind of a model is good when the input slews are kind of all reasonable. Input slew, see when you size everything to be about 4, fan out of 4, then the delays you get, the slews, the input rise and so rise time, output fall time, all of them are kind of comparable, and then again this kind of delay model turns out to be reasonably accurate for small changes, small deviations from that. But if the slopes are very different, maybe your effort for one of the gates is very large. One gate is driving such a large load that its output slew rate is really bad. So then this kind of delay model fails there, because the slew rate itself has an impact. For example, you take a gate, we are talking 50% to 50% delay, right? That's what you're modeling and saying it's linear with respect to the load and the size. But if the input itself is taking a long time to reach 50%, then that also comes in and affects the overall delay. So that has to be also taken into account. So then you have the next level of model, which is a little bit more sophisticated, and so on. So you can add more and more as you make the model more and more complex. You kind of have to start relying on numerical techniques to actually solve those problems. But a lot of these, when you're doing circuits by hand and simple circuits, you can, this kind of rules this is a good rule of thumb to use to kind of design your circuit in terms of sizing if you're looking for minimum delay. And you do the sizing, you see, and most often than not, it kind of works. You're done with that. It kind of works well, and you can move forward.